So, Zach, I wanted to talk today about Planck's contribution to quantum mechanics, and specifically the blackbody radiation problem that we all learned Planck solved by introducing quantum mechanics. Not as a whole, but one of the origin stories of quantum mechanics is Planck's contribution. So I had a question about it, which was, what did he do? What was the contribution that fixed it? What was the problem, and how did he fix it with introducing quantized things? So what do you know about like the story? Because I bet you and I thought we knew the same story, and then I guess spoiler alert, it's not what happened. And I read a book that was like 300 pages explaining how it wasn't what happened. So just curious, like, to start off, what's the legend that physics students hear?
Okay, cool. Well, yeah, I have a couple of thoughts, because you kind of just said before, like, hey, we're going to talk about the UV catastrophe and Planck. And so I did some Googling before this and read a few things. But prior to that Googling, I think like the general story I was told in my undergrad was you had this law, like the Rayleigh-Jeans or Jeans-Rayleigh law, that was kind of a classical application of like electromagnetism and stat mech onto blackbody radiation. And that led to assign kind of like infinite energies at these lower wavelengths. And that was a problem because infinite energies doesn't make sense. And then kind of where the story that I heard goes from there to, well, then along came Planck, and he said, hey, I'm just going to try quantizing energy. Bada bing, bada boom. And there it is. This nice curve that fits the data perfectly.
Right. Yeah. And I think the lay of the land before Planck started getting into his stuff, there were basically two laws that explained the intensity of radiation at different frequencies or wavelengths from an object that's at some temperature. So maybe we should back up and just explain what blackbody radiation is first, because then that kind of sets the stage for what the problem that Planck solved. And then, as you said, the UV catastrophe, we'll talk about that. To start, when we talk about blackbody radiation, what we're talking about is an object at some temperature. Doesn't matter what it is. Everything at some temperature that's not zero emits radiation. And when it's pretty cold, or even into room temperature like you and I, or the stuff on your desk, that's emitting stuff in like infrared radiation. That's where like the peak is. And then you can get things hotter, like a star, and things at that temperature emit in our visible light that we see with our eyes. And then you can go even hotter than that, and things get, they peak their temperature, peak their light intensity at a different color, basically. So you're probably familiar with this with like your oven, like when it's on, it kind of glows an orangey color. And then in addition to that orangey stuff that we can see, there's a whole bunch of infrared radiation. In a normal everyday setting, in like room temperature things, the spectrum goes from mostly infrared low energy light into maybe just a little bit of visible light. But if you continue that spectrum and if you work out a mathematical equation to explain it, up in the high energies ultraviolet light, things blow up, meaning there's an infinite amount of energy in those high, by including those ultraviolet wavelengths or frequencies. So before Planck,
or that's the way it was, right?
Yes. Well, yes, exactly. The old way of explaining, there were two equations. So the Rayleigh-Jeans law is one of them. That one worked pretty good at low frequency. And that's the one that when you applied that to high frequency stuff, ultraviolet stuff, it blows up. It shoots to infinity really fast. Can
I make one small caveat here?
Sure. Yeah.
So, I guess one thing of note is that everything does exactly what you're saying. Like, we glow at infrared and everything, but this whole spectrum stuff is all particular to black bodies.
Yeah. We didn't talk about blackbody yet, but yeah, you're right. Should clarify.
Yeah. Which is a an object that absorbs all frequencies and can emit all frequencies just loosely. And so like they're a mythical beast. They're like unicorns. They don't exist.
Yeah. It's an idealization.
Yeah, but we get pretty close. We in like 1896, around the time Planck was working on all this, people were trying to make black bodies, and they kind of did it by making cavities with a small hole in it. So like a shell of something.
Like a little box.
Yeah, where they put a tiny hole, and then they would heat the cavity and look at the light coming out of the tiny hole, and that's pretty darn close to a black body because
they want something that doesn't. If you shine a red light on it, they don't want to see the red light bounce back. They don't want reflecting surfaces, so they would put like soot like on the walls of the box, the cavity, and so that would like make it completely black. That means that every bit of light that's coming out of the tiny little hole was due to just the thermal radiation of the object, rather than the fact that you had a kerosene lantern behind you as you were peeking through the hole. You don't want to see the kerosene lantern's reflection coming out of the hole also. So it just to ensure that all the light that's coming out of the hole is due to the thermal radiation rather than anything else that could be around it. So it's a little confusing because we talk about the star, like a star, our sun is a perfect or pretty close to a perfect black body, but it's clearly not black, right? It's got a ton of light coming from it. But when we talk about it, we're talking about like if we had a flashlight that could reach the sun, it wouldn't reflect back. That's what we mean by black body.
Yeah.
All the light from it is due to its thermal just temperature.
Yeah, it can do both things. It can reflect it can emit and absorb. So, but it's going to absorb whatever light is hitting it.
Right.
But then it's going to turn that into some sort of, thermal energy or something else, and then emit that back, maybe as a different wavelength even.
Right. Yeah, so Rayleigh Jean's good at low frequencies, bad at high frequencies. Good in infrared. It explained it pretty well, fit the data from experiments in that region of light frequencies well. And then at high frequencies, it completely missed everything experimentally. So they like to use it at low frequencies, which most things are, which is why it has any hold at all in terms of a potential theory, because most things at room temperature are low frequency light coming from them. But when you get into high frequency stuff, it messes it up completely. Not even close. But at the high energy, there was a different law. The high energy spectrum was described well by something called, I'm going to say Wien, but it might be wine, and it might be German, so it might be like Wein. But W-E-I-N.
It's E-I. Okay.
Yeah.
I thought it was I-E.
I think it's E-I.
However, whatever it is. Okay. All right.
Yeah. Oh, you're right. It is I-E.
Yeah. So I guess German would be Wien.
Yeah.
Or
you're right.
Wien. I don't know, but whatever.
I say Wien, but yeah. So his law explained the spectrum well at high frequencies, high energy light, that region of something glowing. But there's kind of like a Goldilocks, like that one's too cold, that one's too hot. We need something right in the middle that actually fits all the data. It didn't exist. And these laws existed partially classically. I mean, not partially, completely classically. Like they were trying to derive an equation for the spectrum based on classical mechanics, based on the motions of stuff that creates this radiation, essentially. Yeah, so that's the blackbody physics that existed around the end of, like, middle of 1800s into the end of the 1800s. And then Planck started working on this stuff in late stage 1800s, and then published his paper early 1900s, like 1905, or maybe it's 1901.
Well,
do you know?
His lecture that he gave that was considered like the birth of quantum mechanics was December 14th, 1900.
Okay, perfect. And yeah, so that was a delivered lecture, but then he wrote, like, he had writings on those lectures, basically. He published I think it was like a 5-part series in early 1900s after his actual lecture. But yeah, so that's the lay of the land. And what Planck tried to do, and the way I understood it was, so I think we've covered blackbody, what it is, and then why there are problems. We had the low energy covered, we had the high energy covered, but the middle bit, the like all-encompassing theory was not covered. Planck tried to tackle that. And the way people had done it before was using like billiard ball, kind of like collision type theory. Ludwig Boltzmann, is that his first name, Ludwig?
Yeah, I think so.
He worked out the theory for gas molecules and the entropy of gas molecules by considering collisions with like colliding billiard balls of atoms. That's kind of like the basic picture. And he worked out the entropy of a gas, not to do with thermal radiation at all, but just like talking about atoms moving around and jiggling and bumping into things. And he worked out based on quantizing the potential like velocities they could have, and saying that if you consider a certain number of molecules moving between two certain speeds in these like bins of a particular size, you could work out the entropy by counting like the probability of that number being in that bin of speeds for the gas molecules. So that was really kind of the impetus for Planck to take that idea of quantization. Boltzmann's definitely not like quantum mechanics at all. His is straight billiard balls colliding and working out statistical mechanics from that. But it's really almost the birth of statistical mechanics, the like the counting and binning and probabilities of large numbers of things. And that was a strictly mechanical process. And what Planck wanted to do was take that and say, let's work it from the electromagnetic theory side of things, like Maxwell's equations. He wanted to come up with another way to talk about statistical mechanics without having to resort to Newtonian like collision type theory. That was his original goal. And I should say this is from after Googling like you did, Zach. My initial question was like, okay, what did Planck actually do? I tried to go on somewhere finding an answer that was like, here's what the equation looked like, here's what Planck did to change it, and this is how it fixed it. I thought I was going to just like find a one pager that would explain that. That's definitely not how it works. And what I found were a lot of answers pointing to one book in particular, which I found at my library by Thomas Kuhn, Kuhn. It's called Blackbody Theory and the Quantum Discontinuity, 1894 to 1912. So with that title, it's a pretty dead-on answer to this question of like, what did Planck do? And it focuses a whole lot on Planck and then talks about a couple people who came after him. But he has... So if you pick up this book, it's long and it's very difficult to read. And I blew through every library allotment of time and had to return the book and then check it out again because I'd went through the renewals too much because it took so long to freaking finish this book. But what I recommend is checking the book out, but jump straight to the afterword. So he has an afterword that I guess was an excerpt of a magazine article he wrote that's like 10 pages long, maybe 20. That explains it very succinctly and very well. I'm like, well, crap, I should have just read that because it explains it very nicely. But I did get to see all the history and all his, deep research that this guy did. So
I'm interested because one of the one things I found when I did my Googling and I didn't, I've only been looking into this for like 24 hours.
Okay.
And, you've put some time into this, but I found in 2000 at Boston University, they had like a Max Planck centennial celebration thing. And I found this preprint sort of papers on the some of the lectures that were given there. And this one guy, I need to pull it up. We can put it in the show notes. I think his name was Oliver or something. Kind of had this big, long bit about Kuhn's book, as well as a few other historians and physicist historians on this whole situation. And he kind of ends his lecture by saying, "Yeah, Kuhn's book is just wrong."
Oh, really?
Yeah.
Interesting.
So I'm kind of curious because I didn't read Kuhn's book. But to get your perspective, and then maybe I'll try to throw in kind of what this guy said.
Okay. Yeah, I'm interested. Kuhn spends about 300 pages going through what Planck did, and he in his afterword he described the like quote unquote legend that we grew up in undergrad hearing about. Is that Planck had discovered that restricting energy levels to a discontinuous spectrum was essential to the derivation of the blackbody radiation law he had introduced shortly before. So he introduced a law. I read a different book by somebody named Douglas Stone, who said that Planck gave a talk and presented his new blackbody equation following from Maxwell's equations, like kind of like an electromagnetic approach to this rather than molecular and like colliding molecules, stuff like that. And somebody came up to him and said, hey, these guys are going to like not take you down, but they're like, there's problems with your derivations. And this is what people are presenting today in this next iteration of the theories on electromagnetic radiation approaches to blackbody stuff. And so Planck was kind of like given a heads up that like people are going to like try and refute your equation. And so he went home and like spent a while like working on his original equation and then tried to go back and like explain it better the next time. So he came prepared. And what he did for doing that, and that's kind of like the time crunch and the sometimes he's described as being like desperate, like he just had to do this change, was to like throw in these like quantizations. He came back to the next iteration where the people were going to refute his earlier work and say, and said, here, this is how it works. And I have to do this like quantization thing to make it work. And Boltzmann did something very similar, which is what the first part of this, I'm going to call it the Black Book because it's just a large black cover. Okay. And it's called Blackbody. I always just call it the Black Book. The Black Book spends a lot of the first chapter or two talking about Boltzmann. Like the first early chapters are all about like Boltzmann's theory because he draws a lot of connections between Planck and Boltzmann's work and saying that Planck had to go, or not had to, Planck went into statistical mechanics of the molecules of that little box, that cavity thing, to explain the spectrum of light that comes out of a blackbody cavity. And he quantized the molecular vibrations of the molecules that make up like the wall of the box, if that makes sense. And he did stuff very similar to what Boltzmann did in terms of counting. And there's something that he said, that Kuhn said, that I never really got a handle on, but he said Boltzmann's bin size, like the range that molecules could have in their speeds, the size of that little range drops out of the equation. So he never really had any reason to worry about it. Like you can make it arbitrarily large or small. But in the Planck theory, the size of the bin mattered. And that's where his like, kind of where his like Planck's constant falls out of. Like there's an extra parameter that sticks around all the way to the end. And Planck is, what I really like about the book is how it explained, or it demonstrated Planck being a very good scientist. Like he didn't just throw out things because he's like, well, I don't want a rogue constant. I'm just going to argue it away. He just kept it in everywhere. But he's like, I don't know what it means, but here it is. I don't want to get rid of it. I thought that was interesting. And it speaks to Planck, I think, being a very good scientist. Yeah.
In this like lecture paper that I read, so it's, I just pulled it up. It's, I guess it's Oliver Darrigal. We can share this as well. Mm-hmm. But one of the things that he kind of went over in when I was reading this was that maybe it's a small difference, but Planck, he was saying, didn't really actually concern himself with the molecules themselves, but like just kind of said it's an arbitrary oscillator. Like he didn't care about the details of what it was, but just that it was an oscillator of some sort. And that was like part of why he was able to kind of, I think, do some of this, like separate himself from Boltzmann, who was very focused on like what the actual things were.
Mm-hmm. Right. Yeah. Yeah. Planck was all about the electromagnetic part of the radiation, not so much like the thermal motion of the stuff inside the resonator cavity. But this book and then another book that I read, the Douglas Stone guy, both of them go on to say like Planck didn't really do anything with he never said that there is now quantum mechanics or like things are quantized. Planck had to I keep saying Planck and Planck. Planck had to divide up the bins. He had to make bins of possible energies, just like Boltzmann did. The difference was his being like stuck around through the whole thing. But it was Einstein, both Kuhn and this guy Douglas Stone both point to Einstein as being the one who recognized that, like, wait a minute, it's not just like a little massaging of the equations that leads to this. It's like things are actually quantized. And Einstein, I think we all know in 1905 was the one who came up with like the quantum of light, which he based on readings of Planck's papers. Like he took it to its logical extreme, the stuff that Planck was saying. And that, I think, was the actual birth of quantum mechanics. And that's kind of the whole thesis of Kuhn's book, is that it's not Planck. Planck did that in his equation, but like it really was Einstein who like pulled out of it. Like, no, things are quantized in ways that we're not recognizing here.
Yeah. Like one of the parts here that this guy talks about in kind of to bolster that statement is, Planck pretty much says there's this small energy, he calls it epsilon, and it's h times the frequency, Planck's constant times the frequency. And but then there's an energy for the whole system that is divvied up over n resonators. I said oscillators earlier. Resonator was the word, I guess, is what they used.
Yeah, Planck used to call them oscillators and then changed it to resonators later.
Oh, interesting. Okay, I didn't know that part.
Or maybe it's vice versa, but yeah, he used both.
But so he said, if you take the total energy, over these n oscillators and you divide it by epsilon, you think, okay, if each oscillator has a quantized number of energy of epsilon, right? Then when you divide the two, you should get a whole number, because you should be getting, a whole number times epsilon, or h nu is the energy. And I guess in one of his papers, Planck says, when the thus computed ratio, that's the energy over epsilon, is not a whole number, one can take for p a neighboring whole number, p being the ratio.
Right.
So he basically just said, like,
it's close enough.
But you don't always get a whole number. Meaning,
right.
Is it quantized? Because if it's quantized, it has to be a whole number.
Right. So by admitting that sometimes it might not come out to a whole number, then he's kind of like, well, it's not really quantized. It's close enough. With large numbers of things, we'll get a number close enough to a whole number.
Yeah.
I think both Kuhn and Stone had the same quote, and that's like the piece of evidence that they point to. A lot of historians, I think, point to and saying like, well, Planck didn't really recognize the quantization. It came later. And yeah, I think it took an Einstein to claim, no, it's not just the molecular energies in being certain bins of a particular size that's quantized. It's the light itself that comes off of those molecular vibrations that lead to the light that we see. The light itself is quantized, and the vibrations give off energy in quantized little packets of light. And like, that's all Einstein, like 100% Einstein. So yeah, I think Kuhn's main point is like, it's not Planck, it's Einstein who like actually figured out the quantum part of the quantum mechanics from Planck's theory. He just really took the idea that Planck put forward and ran with it. And it's interesting, like talking about originally the three laws that we had. Well, the two laws, the Wien displacement, the Wien distribution law.
Not displacement.
It's not displacement. I know I messed that up too. For those familiar, the Wien displacement law is kind of related. It talks about the peak going as a function of the temperature. Those two things are related. The peak frequency, the brightest part of the spectrum. But he has a distribution law. That's the one that we're talking about that works good at high frequencies. And then the Rayleigh-Jeans one at low frequencies. So Planck's equation, he derived from thinking about the entropy of electromagnetic radiation. And he had an equation. I'm going to kind of bastardize this a little bit, but it's pretty close. He had an equation that had two parameters, and he figured out what the two parameters were that best fit experimental data. And one parameter was Planck's constant, or related to Planck's constant, maybe like by a multiplication factor. And then the other constant was related to Boltzmann's constant, K, that comes up in StatMech stuff. So, he like fiddled the equation and fit them to data, and he got out Planck and Boltzmann constant. And he's like, these are two new constants in the world. One's related to the work of Boltzmann for the entropy of a gas of molecules. And then the other one is a new equation, or a new constant that we don't have any relation to. Like, I don't know what this means. There's no physics behind it, but it's a physical constant for, and he recognized it as the action of a system, like the stuff you do like Lagrangian mechanics with, minimizing your action.
It's got units of action, joules, seconds.
Right. Energy, time, position, momentum, that kind of stuff. So yeah, that was his Planck's constant. He named it and he said, here it is. I don't know what it means. And then Einstein was the one that applied it to the photoelectric effect and said, hey guys, check this out. It should, if light's quantized, have, what we call now the work function, where there's no light being emitted when you blast a piece of metal with light up until a particular frequency of light. Then you're going to start seeing light or electrons coming off the metal, and it's going to increase as you increase the frequency. And that is going to be a linear relationship with the slope equal to that constant Planck came up with. Guys, go check this out. And like, no one could do it because the experiments weren't good enough at the time. And then eventually they're like, oh yeah, that's totally what happens. Yeah.
This Derek guy, he kind of has this nice table that talks about these three levels that historians kind of fall into when it comes to this whole Planck quantum bit. Mm-hmm. He said, there's the discontinuity group who, those are the people that think, okay, Planck knew exactly what he was saying, and that he was, saying that there is a quantized system of energy, so that it's not continuous, hence discontinuity. There's an indetermination group who said he really didn't know what was happening, but he didn't believe one way or the other that everything was continuous or not continuous. He's just kind of just doing what he could, and working with what worked. Mm-hmm. And then there's a continuity group, which is where he puts Kuhn, who believed that Planck just thought it was continuous, and that even though his thing fit, it wasn't going to be correct. Like I watched the PBS Space Time kind of on this, mm-hmm. and they mention in it that I don't know where this came from, but they said that Planck thought H would actually end up being zero, right, and not matter. Therefore, nothing is quantized.
Yeah, I think the Einstein edition and the other book by Douglas Stone, not the black book. Douglas Stone's book talks about Einstein being kind of ridiculed for his quantized light theory after he had come up with relativity, and everyone's like, wow, he's so brilliant. He's trying to get positions at universities, and people writing letters recommending him, and they have to put a little caveat. They're like, even though he still thinks the light is quantized, we can't hold that against him because that's the cost of being brilliant. So they're still writing to recommend him positions at universities and saying don't worry about his quantized light thing. That's not true, but we just have to, it comes along with Einstein being a genius that he has these outlandish ideas about light.
That's funny.
So people still didn't believe him.
Wow. Yeah. And then he wins. That's what I feel like most people don't know, but that's what physicists know, but general public does not know that that's what he actually got his Nobel Prize for.
Right.
Yeah.
Not
relativity.
Mm-hmm. Yeah, the relativity. I think the line is and other contributions to physics. It's what he was awarded the Nobel Prize for. The phrase was his discovery, or for his services to the theoretical physics. Oh, his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. So he got the Nobel Prize naming the photoelectric effect in his for his services to blah blah blah. But then to theoretical physics just broadly, especially photoelectric effect. Yeah, so I was shocked. I shocked in over the course of several months, I guess, reading this book to find that there isn't a quick fix that Planck just threw quantum stuff at an equation and then there it was done. He's the birth of quantum mechanics, which he is, but it was continuous.
Kind of like, so I guess I said I was a little too harsh earlier when I said I wouldn't necessarily characterize this paper as saying Kuhn was wrong in what he said, but it kind of just talks about like different ways to even view this whole picture. Mm-hmm. And he was kind of saying a lot of the people that kind of agree with the story that we heard originally, that Planck knew what was going on, and he found he understood that this was a quantized energy system, that he was doing something interesting and revolutionary. That kind of comes from, like, if you look at the broader picture of what happened with that idea, like, even though maybe he didn't specifically intend for this to be the case, the fact that people interpreted his idea of this quantized energy in a bunch of different ways led to the birth of, it led Einstein to be able to make his prediction. Right. And, it contributed. I think this might be misquoting the people here, but this, paper kind of talked about like people like Schrodinger and Heisenberg and stuff, like also got, ideas from reading Planck's paper. And therefore, like, I think their argument, at least in this paper, isn't like, okay, so one way to look at this historically is that even though maybe Planck didn't know exactly what was going on, that he's the one that led to this happening by coming up with this idea in the first place.
Right. Yeah. And the Black Book talks about Einstein as one person who picked up on the like implications of Planck's work, and then another one was Ehrenfest, who's a name you might recognize.
Oh yeah.
He was somebody else who worked out. He's like, okay, if Planck's work is true, if we can like believe this stuff, like here's what it actually means, and like tries to work out like maybe an origin of it, and ended up similar to Einstein being like, okay, stuff's actually quantized. Like we need to pay attention to this concept. And then I believe it was Lorentz who was, I think, one of the more important people in terms of just making this more widely believed, because like he was a big name at the time. Einstein was not a big name at the time. So the fact that Einstein came out with something very important at the time, it didn't really have the big impact that Lorentz's work had. So Lorentz was like believing it also with Einstein kind of around the same time. And I think they had talked to each other, but Lorentz was the one who was like, guys, this is big. We need to pay attention to this. And then it kind of caught on. And that was like, yeah, like late, like 1910, like around there, approaching 1910, that stuff from Lorentz and like other people started to really catch on. And then it was really like into the teens of 1900s that quantum mechanics took off until like, 1920s when it was like formalized by most of the people that we know about today. But the whole thing, it took a while for it to catch on, and it took a while for people to realize what the implications were.
Yeah. It wasn't like he just wrote this, he gave his lecture on December 14th and then boom, everyone went, oh, quantum mechanics is a thing,
Yeah.
It took time. Just like, I think like all great ideas.
Yeah. I was also surprised that Planck's original like mission was to work out the entropy of thermal radiation. And like that was his goal. He wanted to figure out how to explain entropy, like not just entropy, but the second law of thermo specifically. He wanted to come up with an equation that showed the second law of thermodynamics using essentially Maxwell's equations. And that's like how it started. That's like where he wanted to go. He didn't want to have the second law of thermo based. If it's truly a universal law, he wasn't happy with it just being confined to billiard balls of molecules colliding and like counting stuff like that Boltzmann was doing. He's like, we should be able to get to it from electromagnetic direction also.
One of the things I read is that he was not happy with like a statistical version of it, that he wanted, I don't know what the opposite of statistical is.
Yeah.
Deterministic version.
Right. Exactly. Yeah. So if people are interested in reading more, have a go at the Black Book. Again, Blackbody Theory and the Quantum Discontinuity by Kuhn. But I would recommend skipping to the afterword to get an overview of everything. And then I would recommend this Douglas Stone book. That's much easier to read. And he has like an hour-long lecture talk that you can find online. We'll put in the show notes. but his book in particular is accessible and enjoyable to read. It came out after the Einstein bio, and I think he kind of talks about that big biography. What was the guy's name? Do you know who I'm talking about that did the big Einstein biography book maybe like 10 years ago?
No, I don't.
More than that. There's probably lots of Einstein biographies and Steve Jobs biography, but there's one guy who's like the biography guy who like did a ton of work. Yeah.
I just Googled Steve Jobs biography. It took me to a webpage and it said authorbiography.com. So not that.
Yeah. So it's Walter Isaacson is the biographer who did the Steve Jobs and also the Einstein biography. Both are very good books.
I'll post this preprint from, there's actually a few people in here, and I actually want to talk about another paper in here that I read a little bit. But sure. Oliver Derrigal is the one who wrote the paper that's kind of, he kind of explains all points of view, and he lands more on between Planck not knowing that he was making this big prediction and like kind of being ambiguous about it, and just still believing that everything was continuous. But he kind of explains a lot of people's different points of view on this topic, and it's pretty short. It's like 10 pages.
Cool. There was a point I wanted to bring up about people refuting Kuhn's work. And I'm trying to remember the physicist that he specifically named a physicist who was like, that's not how it worked. And it wasn't Derrigal. It was somebody that I recognized, and it might have been Summerfield or somebody around that.
I read ones with about Summerfield, another, and I think Aaron Fist as well, Klein. Here, let me see if I can let's see, Needle. Most of these I don't think are physicists.
These are people who
Rosenfeld,
who refute Kuhn,
or who
like his
on the
they don't believe that story. Yeah.
The ones that don't, I guess that this guy lists would be Klein, Hund, Jost, Rosenfeld, and Jammer. But I do remember reading something about Summerfield somewhere too.
So one of those people Kuhn explicitly writes about, and he says people misremember the history, and he has an example anecdote that's kind of funny about Bohr, where I guess Kuhn had interviewed Bohr when Bohr was alive to ask about the origins of quantum mechanics, and he interviewed him 3 times, and the first time he asked him a question like, what were you thinking when you wrote this? Or I don't know if he phrased it that way, but something along those lines. And Bohr's like, I would never write that. That's so wrong. That's such a stupid statement. And he as he walked away, mumbled that's a stupid question. So Kuhn went back the second time and asked him a slightly different way, the same question. And he's Bohr still is there's no way I would write that. That's totally wrong. That doesn't make any sense. And then the third time he went with the paper that Bohr wrote and showed it to him. And he's like, look, you wrote this. What were you thinking around that time of writing? And he's like, oh, who knows what I was thinking back then. And so Kuhn's point is that people misremember the history after in the origin days, you're saying a lot of stuff and some of it could be wrong. And then looking back, you forget those wrong things because they're wrong. And so they're not important to what you were discussing, but the correct parts end up being remembered much more. And so he's saying people that are refuting him are saying, well, you should probably look into the actual texts and letters and exchanges that people have had around this topic, which is what Kuhn does. He's a historian, not a scientist, and not, his whole thing is going to origin sources, letters between people and explaining things in that way. And so scientists that are saying that's not how it happened, he's kind of saying well, you should really go check the sources.
Yeah. I don't have all the details, but yeah, that's, this paper kind of talks about that as well, and kind of has different. This guy was just trying to explain kind of all of the ideas and how to do it. But yeah, he had one statement about. I don't have a dog in this fight personally, but he had this one point that he thought was impertinent, where I wish I could find it, but it basically said. That in Kuhn's argument for this, kind of you have to think of Planck as consistent in one state and then inconsistent in another. And that kind of led to a contradiction.
Kuhn, besides the Bohr story of being interviewed, he talks about Stern from Stern-Gerlach experiments that are kind of one of the first signs of quantized spin states. He interviewed Stern and asked him about did you know you were going to find this, separation of stuff? And he's like, honestly, no. We were just doing the experiment and wanted to see what happened. And that's what we saw. So everyone points to it now as that's the definitive experiment that showed quantized spin states. And Stern said, we didn't set it up to show that. We just wanted to see what would happen, pretty much. And so, yeah, he's like, sometimes people look back and be like, oh, they're brilliant. I mean, obviously they're very smart in setting up this experiment and knowing where to look, but it's not always with the intention of being this revolutionary act.
Right.
I found this story, this I don't know, somewhat refutation of the history that we're taught in school of Planck just being this, I don't know, the word that gets thrown around is reluctant revolutionary, where he didn't want to be upsetting the world of physics, and that's pretty much not what happened. And he didn't come in and say oh, everything is quantized, the light is quantized. He didn't talk about the light being quantized. He was only just binning molecular vibration energies in terms of a counting thing.
Yeah, one of the ways that I kind of got when I read through this is that he did this because he just we needed to try something, but then wasn't certain, kind of just what it meant. And I think when people say what was the word that you used earlier? He was desperate, right? To make something work. And I think kind of from what I've read, it seems a desperate person, they don't, try something and then go, oh, this is the new theory of the entire world, right? If you're desperate and you try it, you go, I really hope this is accepted and it works, and it it kind of sounds like that's kind of, he just said this works and tried to figure out what that meant as well.
Right.
Not the story that we're told where he was oh, this works and everything's quantized.
Exactly. Yeah. He's like, guys, trust me, everything's going to change from now on. It's that's not what he was going for. He was really just explaining his theory of, I mean, again, I kind of mentioned him keeping the rogue constant around as being a sign of a good scientist, but I think the story really shows how he just believed what he was working on and just kept trusting the math to work, whatever it worked out to be. He's like, this is what it's saying. I don't really know what it means, guys, but somebody take a look, please. That kind of way. And he was in a position of authority enough that people listened to him. And he was a brilliant scientist.
And so kind of along those same lines, a part I want to add to this whole conversation is in the same preprint of these lectures here, Dieter Hoffmann has a paper that he has written. It's called On the Experimental Context of Planck's Foundation of Quantum Theory. And basically, he just goes through, when we are told this story, we're only told about Planck and, I guess we've also talked about what Boltzmann and what Lord Rayleigh, or is it Lord Jean? I don't know, one of them's a Lord, and, all these theorists, basically, and how they did this whole thing. But behind the scenes, there is, some incredible experimental physics happening. That we don't ever talk about. And this guy kind of highlights some of it.
Oh, that's cool. Kuhn's book does not, and I think he talks a little bit down about experimentalists at the time, saying that maybe one of the reasons that it didn't catch on as much was that experimentalists couldn't do the experiments to show with that kind of precision. I could be misreading that, but that's the impression that I got.
Well, I mean, I kind of feel like we have some evidence, at least, that there's some of the opposite, right? There was one thing that I read in this paper that was saying apparently Kirchhoff. So Kirchhoff was also a big blackbody radiation person. Mm-hmm. He made this suggestion about how to make a blackbody early on, and like no one really listened to him, I guess, for a while. Like I think he did it in like the 1860s or 70s, and no one listened to him. And then they tried other things, and finally, when they ended up making a blackbody, it was very similar to what he described in his paper. And it took like 30 years or something. So there was that, I guess. But these scientists at I don't know the German name. The PTR is just the
Polytechnic something. I think
it's Physikalische Technische Reichsanstalt. I don't know. I'm sorry.
Okay.
Please excuse my bad German. PTR. They're close to. I guess they're like within Berlin as well. While Max Planck is working on this stuff, and let's see. The guys that he talks about here are Ferdinand Kurlbaum, Otto Lumer is kind of the big guy. Ernst Pringsheim, I'm really sorry. Heinrich Rubens and Wilhelm Wien as well.
Okay.
So these are kind of the guys that were doing the experiments behind the scenes to show some of this stuff. So like they made a black body. Like they were one of the first groups, it sounded like, to actually make something. And basically they started with a sphere that they like had a little hole in, and they would put it in like a heat bath or something, where they would coat the insides, like you're saying, with like soot, or they would make it out of graphite. And they had to develop a new photometer to actually be able to have more precision than what was out there. And then they decided, like, okay, this idea that we have for these black bodies isn't good enough. They ended up with this cylindrical tube where they put a coil of platinum at the end, and then they would put like 100 amps apparently through this like coil of platinum to heat up the cavity, and then look at the light coming out of it. But like, I mean, if you just kind of think about this a little bit, like, I don't know if you've looked at a plot of Wien's or Wien, whatever, his approximation law. What did we call it? It's not the displacement law. It's the distribution.
Yeah.
So if you look at that distribution versus Planck's distribution,
it's not that far off.
It's not that far. Yeah, exactly. Like compared to the Rayleigh jeans,
right.
like it's so obvious that doesn't work.
Right. Yeah, but Rayleigh jeans just explodes right out the gate, goes to infinity pretty fast.
Yeah. But Wien, his law is like not terribly far off. And it wasn't even known that it was wrong until these guys came along and made really precise measurements. They stole this photometer type device. They didn't steal it, but they used the idea that this astronomer came up with. It's called a bolometer, I guess is how you say it, from this American astrophysicist Samuel Langley. And basically it was a wheatstone bridge that had 2 platinum strips on it. And I guess platinum is just a great material because it was used all over the place. But one of the interesting things about platinum, we still use it to this day, is its resistivity changes as a function of temperature.
Okay.
So they could shine when light would hit it, its resistance would change. And a wheatstone bridge is really good at measuring changes of resistance.
Okay.
So they could measure the tiny changes of resistance of this platinum wire, and from that figure out the temperature change.
Huh. Oh,
and so
it all depends on the precise temperature measurement, obviously, because you want a good, like, crystal clear distribution at a temperature fixed, right?
Yeah.
Because if your temperature is fluctuating all over the place and you're trying to get a precise like curve on like a spectrum distribution, it's going to be really tough to say like definitively this part of the line is the same as that other part of the line. Right. Is my guess.
Yeah. You basically want to be able to know exactly what temperature you're looking at. The to make these small changes between to find out that Wien's law is not right. And apparently this device could measure, like it has a precision of 10 to the minus 5 degrees Celsius. And then apparently, like I think the thing I saw on Wikipedia is that it was able to spot the thermal radiation of a cow a quarter mile away.
Wow.
That's how accurate this thing was. And it was used originally for astronomy, right? So like to look at stars and stuff.
Yeah.
But so they had this idea for this device and they're like, that's not good enough. We need to make it better. And so they like literally started getting into like almost modern fabrication techniques, where they like sandwiched this piece of platinum with silver until it was like one piece of metal. Then they cut out a particular pattern to give it kind of more surface area to measure, or not surface area, but length to measure the resistance change over, and I guess surface area to pick up more light and heat as well. And then they would dissolve off the silver, and then they had this like micron thick piece of platinum that they would use, that they would have to blacken and then shine light on. And their version of it got to like 10 to the minus 7 degrees C that they could differentiate. And yeah, apparently they spent, and this is all happening in, I think this is cool too, in like 1896 to like 1900. Mm-hmm. And then they realized, like, okay, they want to look at, like you were saying earlier at the start of this, a lot of the heat that given off at like normal temperatures is infrared. So they had to use like the right optics to not absorb infrared.
Right.
So they like had to choose their optics, and they like changed lenses for mirrors. That way they're not absorbing anything in the lens material. And just like a lot of incredible engineering and thought went into this to make these measurements.
Where is this?
This is in Berlin.
No, sorry. Where were you reading about this stuff?
This is on, so the paper that I found, the preprint.
The Oliver Derek guy?
There's actually 3 papers in there.
Oh, okay.
And this is just another one of them. It struck me as interesting because it's, what I wanted to know when I started reading this is like, how did they make black? Like how did we measure this?
Right.
That was my curiosity. So yeah, I instantly went to this paper.
Cool.
Basically, like, I guess at one point they went to Planck, and they're like, hey, we have this data that's showing that this isn't right. Like like Wien's formula doesn't work. That's part of the reason too why Planck was like, he kind of dropped other things, like, okay, I'm going to do this,
right,
and started working on it. But he kind of, apparently he had some knowledge ahead of everyone else, because this was before they published their results.
I see.
That
something needed fixing.
Yeah, exactly.
Right. Huh. I thought, so this is all in Berlin, right? And then the experimentalists being in Berlin, and then Max Planck being in Germany. Was he at the same university?
PTR? So PTR is I don't know exactly what it is. It's its own thing. Facility. I don't know if it's like a government research facility or something.
Right.
And then, but Max Planck was at a university, I think, in Berlin.
Oh, okay. Yeah.
So they were close.
I thought an interesting part of the history was how a lot of the work was being done in Germany in isolation from people in like the UK. So like Maxwell's Scottish, and then people like in the UK science area, journals that are written in English weren't communicating with the journals and scientists necessarily in Germany, and so they weren't like finding out about each other's research unless somebody actually traveled there and like went to a lecture or something like that and like came back with information. It wasn't as widely distributed where like, they wouldn't publish the English journals in Germany and the German journals in the UK. So they wouldn't necessarily know what each other are doing.
Yeah. I read somewhere that there was another group that was doing the same or very similar things as PTR was doing as well. This Lammer guy, I guess, was the lead who led through all of this. And then I think it's also like, it's, so I want to just highlight some of the, experimental physics that went on to make this possible. But additionally, like, I think it's a cool illustration of science in general, right? Where we have a theory, we make a prediction with that theory, and then we make a measurement and say, hey, that's the reality doesn't agree with the theory. Mm-hmm. And so we okay, all right, let's nix that. Let's try another theory. Then we do it again and we go, oh no, wait, that doesn't fit either. Mm-hmm. So we have to nix that. And then finally is, when Max Planck figures it out, it all comes together.
Right.
But like, it's a good illustration of this back and forth that we have between theory and experimental. And I think back then we didn't have necessarily this, the same separation that we do now between experimentalists and theorists.
Right. Yeah. I think, and another point of the greatness of scientists at the time, I don't know, maybe probably the same now, but Max Planck was the head of the journal that Einstein published his paper in 1905 talking about the photoelectric effect and the quantization of light. And Einstein talks about Planck, but I guess the Douglas Stone book kind of offhand makes a comment that Einstein was nicer to Planck than maybe he wanted to be, and that was because Einstein had a friend who like kind of helped him write his paper, meaning like proofread it and bounced ideas off him. And that friend, I guess, talked Einstein out of like being really harsh to Planck. And so Planck got Einstein's papers, which were clearly like kind of talking about Planck's missing the point of his own work, and let the papers be published anyway, like in the journal, and saying like, yeah, it's fine. Like, he's accepting of that, even though maybe it was a little bit it's not against Planck. It wasn't like saying Planck was wrong. He's just saying, missed the point, buddy.
Yeah. Yeah. I don't want to go off on a big tangent, particularly because I don't know too much, but I've heard, like now we kind of combat stuff like that by having like these blind anonymous reviewers of papers, right?
In theory,
journals.
But yes.
Yeah. But then I've heard, that some fields get so small,
you know who
that
they
it's,
are.
Yeah, exactly. And you're able to, you don't have that anonymity anymore.
Right. Yeah, the book specifically says nothing has survived of the like journal's records of the reviewing of Einstein's paper, so they don't really know what Planck thought or if he even like signed off himself. But he was the head of that journal, so in some respect, he was in charge of Einstein's paper coming out. But yeah, everything I've read about Planck says the dude was super brilliant and deserves all the accolades that he gets for being the founding origin of quantum mechanics, like you said, if not only because people took his work and built upon it and took the implications maybe a little bit more seriously, but to like a larger extent than Planck envisioned with his publication from the beginning. Well, cool. I had fun learning about this stuff. I like I said, I mean, I kind of got the like shock part like pretty early on in my Google searching, but then wanting to read more, I was like, oh, that's actually pretty interesting history that I wasn't aware of.
Yeah. Along these lines, if we're interested in this still, I noticed in this Oliver something, I really wish I had his last name just memorized at this point. Yeah, there we go.
I have it written down this way.
Oh, okay. Yeah. He talks about these other kind of versions of this that I thought maybe would be interesting to talk about in the future. But like this was the first one that caught my eye. Was he said, consider for instance the case of J.J. Thomson, who discovered the electron. Historians should, he puts in parentheses, know that the new particle described by Thomson in 1897 had less resemblance with the modern electron than the one announced a few months earlier by Emil Wiechert. So I thought that was kind of interesting. Like I wonder how many times we kind of have these, stories that aren't, like that have kind of built up their own mythology.
Yeah, mythology. Yeah, that's a good word for it.
That's not really like kind of the exact way it went down,
right, Right. Yeah. It's similar with a kind of bad version of this, but I think Feynman talks about it, is the Millikan oil drop experiment, getting the proper, do you know what that is? Like the charge to mass ratio of the electron?
Yeah, the milk and oil drop experiment. I know this one well because we do it in one of the labs that I run.
Yeah.
But it's he atomizes oil into like tiny, tiny particles, and when you do that, just them traveling through the air, they'll pick up a charge. And so you atomize it into two capacitor plates, and then you put an electric field in the between the you turn on the capacitor basically, and you kind of time how long the velocity of the particle, and you apply all the force equations necessary to it, and from that you kind of find that they have you get a discrete charge. So Millikan's experiment did two things. It first discovered that that charge is in discrete chunks as well, and that he was able to measure the actual value of it. But there's
of the charge itself or charge to mass.
Just the charge itself.
Oh, okay. Cool.
Yeah, I think it's the Thomson tube that I don't know if that's as different than the actual discovery of the electron, but the Thomson tube, that's the one that you probably have seen where you have the tube or with the Helmholtz coil around it.
Oh, and you can deflect. Yeah.
That one is the one where you can measure the charge to mass ratio.
And that came before Millikan?
I don't know the order.
I don't know. I knew that they knew the charge to mass ratio, and then once somebody figured out the charge, which could have been Millikan, then you obviously from the ratio you can figure out the mass. So they got both of them done at once. It
must have been Millikan came afterwards.
I think so. Yeah. But the story of this and the mythology, and we hear that Millikan figured out the charge of the electron, and everyone's like, wow, that's crazy, brilliant, first guy to do that. But he was off, pretty far off if you look at what he published as the charge. And Feynman's point is if you look at the publications for the charge of the electron as a function of time, which it's not the charge of the electron actually changes, but the published value asymptotically approaches what we know it to be now, which we say is the actual charge of the electron. It's like a trend approaching what we know now, and from Millikan's data point, it goes closer and closer and closer. And Feynman's point is that Millikan was such a big name in science, we just trusted his value more than anyone else's. And so if somebody did an experiment to try and confirm Millikan, but got a number that's the actual charge of the electron, they wouldn't have been accepted because their number was too far off. You're not close to what we accept now, which is Millikan's. And so the act of science is steeped in these big names coming out with these results and then believing them. But then over time, our understanding was you have to incrementally adjust, but you can't just jump straight to maybe the right answer because it's in conflict with somebody, a big name, their value. Right.
Yeah, exactly. Which is not great, right. But it's hard to fight human nature at the same time.
Yeah. So I think there's probably a lot of examples of that, of our mythology and history of quote unquote history of our fields that end up not really being true, or not the whole story, of course. It's always more complicated no matter what.
Yeah. And I mean, part of it too is it's easier pedagogically to introduce it with a simple, rather than go through this whole story.
Right.
You just say, yeah, this happened and then this happened. And you don't talk about everything in between.
Right. And Kuhn is a historian who covered the origins of quantum mechanics, and his role was to interview living quantum mechanics physicists who were at the beginning of quantum mechanics. And Planck wasn't alive when he did that project, but he did go back, he said, and read the original Planck lectures. And when he was doing that project, and he's like, oh yeah, that's the quantum mechanics papers. And he read them and he's like, got it. Totally understand. Planck came up with quantum mechanics. Check. Moving on. Let's start interviewing people. But then afterwards he went back and reread them, and he's like, oh, he doesn't actually say anything that's physics is quantized. It's not in his papers at all. And yeah, it came out later. I think that was the main takeaway from Kuhn's reading of Planck's work. And I bet even the people that maybe are against Kuhn would agree on that point, that Planck didn't just outright say quantum mechanics based on my papers. Obviously, the term wasn't in there.
Yeah. That's one interesting point too. That one of the, I think it was Needle in this. What's his last name? Derrigal.
Derrigal, yeah.
In Derrigal's paper, he references another historian, Needle, who just outright won't talk about anyone. Like if anyone has a point on this, he won't talk to them if they are talking classical versus like quantum, because like when this happened, there wasn't classical versus quantum, like that didn't exist.
Right. Well, cool. Well, my original question ended up being not answerable. So I did want to see an equation, like something like the Vine distribution, which was continuous and wrong, that I thought was going to blow up in the ultraviolet catastrophe. But that's not at all what happens. And then Planck came in and said, no, make it quantized, and then it's not going to blow up. I thought that's what was going to happen, but apparently that's not at all the case. not even close.
It was, hey, we're off just a little bit in these small wavelengths.
Mm-hmm. Yep. So I asked this question for those that don't follow us on Instagram. I asked on an Instagram story if anyone had a reference for this question, like a long time ago. And then I finally did some digging myself. But follow us on Instagram at @thehyperfine. And sometimes I ask questions there. So if you have an answer, I would appreciate it. And then maybe we'll talk about it on the podcast. So check out The Hyperfine on Instagram.
Cool. And you can also follow me. I don't post much, but I'm at FizzZax on Twitter.
Mm-hmm. Yeah, so the show's at The Hyperfine, but I'm at Like Tortilla. Derek Padilla, Like Tortilla. Cool. Well, yeah, I'm excited to step into recording more frequently. Hopefully we get some episodes out. We'll talk about some topics offline. See what we're going to talk about next.
Cool.
All right. Thanks, Zach.